So this right here is a portable vacuum cleaner, well, fairly typical device for this day and age. It's a handheld one. It has integrated batteries, and you can plug it into a larger piece to actually turn it into a floor vacuum cleaner. And this one has developed a rather peculiar fault, namely that as soon as you try to power it up, it shuts down. I took it apart the other day, found out what's the fault, ordered some replacement cells. So this is what the video is going to be about. I'm going to show you how to diagnose these faults with lithium battery packs, and I'm going to talk about the electronics for a bit. Let's get to it. This particular model is quite easy to take apart, maybe except for a few clips that hold it together. To get to the battery pack, you just need to get to the end of it. You take off the lid where the filter goes, you take off the filter, and then basically there is one screw down here which screws down to the rest of the handle, and then there are a few clips that you simply have to undo with a bit of applied force. Inside of this handle there's the battery pack and the control PCB, which is snapped to the top of it. I have separated these two because I was doing some measurements, but generally they are quite trivial to snap together and unsnap. So let's take a closer look at the battery pack now, and I'm gonna show you what the fault is. So this battery pack is fairly standard. You've got 7 18650 cells, which are probably the most ubiquitous type of lithium cell out there. They're being used in pretty much everything from laptops to electronic cigarettes. Which makes them quite universal and quite cheap and easy to get. So the way these packs are normally wired is they are all in series, which means that if one of the cells goes out, as you say, basically develops some kind of a fault, discharges too much, or due to some other reasons stops behaving like a cell, the entire pack is pretty much dead, as you would say. Which is a shame, because one bad cell can take out the 6 other good ones, and pretty much 6 perfectly good lithium cells end up inside a landfill. The way this pack is connected to the main board is that you have all of these cells are connected in series, as I said, and you have these two thick connections which are rated for the current, because, well, the motor pulls a lot of current from these. I think these are 20 amp cells, if I recall correctly. And these two will basically go to the main board, battery plus and battery minus over here. But at the same time, the battery management system, there's a special IC which is right here, needs to monitor each of these cells separately. So from each of the cells, which are all in series, from each of these cells there is a wire which goes to the main board, and that wire is being used by the battery management system to measure the voltage across each of the cells. This is pretty much how this looks like. So as I said, you have 7 cells in series. The thick line is the high current path, and then, like in any other BMS, from each of the cells you have a small low current sense connection, which is used to sense the voltage. In a similar manner, like with this BMS, this is like an off-the-shelf BMS for 2 batteries in series. You have B minus, BM, and B plus. And B minus goes to the minus of the cells, BM goes to the middle, and B plus goes to the positive end of the battery. So this is basically the same deal, but you've got 7 cells instead of 2. So of course you've got B1, B2, and so on. And now if the BMS wants to measure the battery of each of the cells, it's gonna do a measurement of B1 relative to B minus, then it's gonna do a measurement of B2 relative to B minus, or relative to B1. That depends really how they implement it in silicon. And basically with this setup you can measure or calculate the voltage of each of the individual cells. You can use this to monitor them while charging, which is a rather important thing to do. Because if one of these cells gets some anomalous voltage, it means that there is an issue with it. So now let's go ahead and measure the voltages of these cells, and you're gonna see for yourself what's the problem with this battery pack. Alright, so I've installed the board back back on the battery pack, because this cable is quite short, and it's generally the most convenient way to measure this, as I've measured this before. So let's see, B minus on this particular cable is the brown one, and B plus is the green one. So if we measure across the entire pack, we get about 20 volts. And then if we go down each of the batteries, we're gonna measure the voltage of the first 6, of the first 5, and so on batteries until we go down to the first battery. So yeah, all of these 7, they have 20 volts across. This pack is a bit depleted because it has not been charged. If we take the first 6, we get 16, so 4 volts below, which means that the last battery has about 4 volts across it. If we go down the next cell, we get 11.9, which is roughly 12, so once again 4 volts below. 7.9, so roughly 8 once again. We go down here, and there's something seriously wrong, because we're measuring across 2 batteries and we get barely 4 volts. Now this would mean that they on average have 2 volts each, which is quite low for a lithium cell, because they generally should cut off at 3 point something. 4 volts is something about 4.2 volts is a fully charged lithium ion cell. So there's only one thing left, and it's to measure the last cell. So between the brown and the black wire, we get roughly 0.4 volts, or even just a little bit negative. So this means that the cell which is the first one in the series, let's call it the first one. So the cell which is between the brown and the black wire is completely broken. Maybe it shorted itself out, or it has faulted open. So if you look up the number which is on this cell, the model number, which is ICR 18650 HD2C, if you type that into Google, you basically get an answer that this is a 2000 milliamp hour 3.6 volt lithium ion battery, 25 amps. And basically, if you're replacing them, then it's important that the capacity and the current capability is going to match, because otherwise, if they work in a pack and one of them has lower capacity, it's going to lower the capacity of the entire pack, because the BMS is going to notice that one of the cells is discharging faster and is going to cut the pack off quicker. At the same time, it's important to actually keep the current capability. I have no idea how much current this motor pulls when it's running, but generally a good idea to replace it with equally capable cell. Otherwise, you risk overrunning the cell with current. These cells alone are quite cheap to replace. This one is 20 PLN. The entire pack with the electronics as a replaceable part was about 560 PLN, if I recall correctly. So let's tear this pack apart, identify which cell was bad, and replace it. So I took off these 2 foam isolators, and it reveals the structure of how this pack is constructed. And it appears that it's being held together by these metal tapes, which are spot welded to the terminals of the batteries. Which is both good and bad news. Well, the bad news is that I have to tear them apart, so I have to undo the welds. The good news is that the replacement cells that I bought, I specifically bought ones which have the tabs already welded, so that I can avoid soldering directly to these cells, which is generally a bad idea. So that's one end gone. I've managed to snap off one of the leaves here, and the other one is intact. Now I have to do the other end. This one. Of course, carefully not to short anything out. So with these 2 tabs released, hopefully I will have enough room to take this cell out. Yep, and now verify it's the right one. Yep, so this one says 0.2 volts, which is basically way below the threshold voltage. This cell is not useful anymore at all. What I do, I don't have any place to give them away to recycling, and you generally cannot throw these into the trash. I just secure one of the ends with electrical tape and put it away. So now we have to find out which way to install the new cell. Generally on 18650s, this end is the negative one, this is the positive one. If you buy a new 18650 or any other cell, they generally come pre-charged, so you can use a multimeter to always make sure, because it's a bad idea to make assumptions about things which are easy to check. So yeah, we got 3.6, so this end is the positive one. Now we have to look at the other cells in the pack and figure out which end is which. The way this goes is you have the minus here, it goes through this cell to the other end, so this is the positive end of the first cell, which means that the second cell has got its negative end over here and the positive end over here. This would generally match. If you follow all these cells, you're gonna find out that the positive end of the last cell is this red wire. So just to make sure I don't make a mistake, I'm going to mark this. So this is negative, this is positive, and it means this is negative, and this is positive again, and so on. I think that's enough. Now, of course, also be careful with bending these tabs because of material fatigue. I've noticed that I've bended this one a few times, so it might snap any time now, which would be a problem. So let's try to install this. Another problem is that these tabs are pretty much orthogonal to each other. These ones are welded in the same direction, but I have to do. Basically, I'm planning to put a lot of isolation tape over it, but I might have issues with actually putting the tabs through. So I kind of have to weave them through the hole, and it's going to prove problematic. So I'm doing this on the negative tab because the body of the cell is connected to the negative one. So even if somehow I puncture this rather thin casing, I'm not going to short out the cell itself, which is just another detail that's worth to keep in mind. So yeah, generally I should be using a spot welder. I do not have one. Soldering to the tabs is somewhat better than soldering directly to the cells. Still not the best way and not the right way, but because the tabs are a bit quite long here, I hope that the thermal stress is going to be greatly reduced. These tabs are going to radiate a lot of heat, that's why I'm using this beefy iron, but basically they are going to help keep the temperature of the actual cell ends as low as possible here. Of course, it would all be extremely low with spot welding, and spot welding is the proper way to do it. But I've put a few battery packs together in my life, and they have all worked all right. So now if you measure between the black and the brown wire, we get 3.6, which is the standard voltage of a cell. I should have probably charged it up to 4, but this is the BMS is going to take care of that. And now across the entire pack, which is going to be around here, 23 volts. It was 20. And actually I think we forgot to include the two cells on the very end, so the entire pack is going to be across here, and that's 27 volts. That must have been 24 before. We've we've replaced one failed cell with a new one, so we've got about 3.6 to 4 volts more. And yeah, basically, so the BMS is going to take the intermediate voltages between these cells from this cable cable here, and then it's gonna take the B plus and B minus basically from the board where the actual high current connections are gonna be. This is surprising because they've saved 2 cables on this connector, and they have a somewhat falsified measurement because these cables and these connections are gonna have some non-zero resistance, and once you start pulling a hefty amount of current through it, you're gonna have a voltage drop on these cables. How big is it? I can't really tell off the top of my head, but if they've done it this way, it means that this cost savings are probably more important than this small little detail. So before we put this thing together, I would like to test it, so I'm gonna connect it back as it was. Battery minus is over here, battery plus here. Yeah, I guess that was the capacitors charging. There is a hefty amount of capacitors on this board. It's going to be, I think, 4 times 47 microfarads in parallel here, just to smooth out the power to the motor. The fuse is 15 amps. It probably means that the motor is going to be around 13 in normal operation, and them putting 25 amp cells here originally is a rather good design with a large safety margin. Okay, so these two are the motor connectors. So for a while I thought I screwed up because I didn't label them. Fortunately they have different connection rasters, so you cannot, so there's only one way to plug them in, which is also a very nice design for manufacturing detail. So they basically go here, and as you can see that these two connectors, they also have a slightly different raster, so that there's only one way that you can plug it in correctly. So if I am right about this, it's all hooked up correctly, and if I press the button it should give some signs of life and maybe even start the motor, so let's give it a try. Yep, so it works, and because there's no filter, it actually spat a lot of dust on my desk from the end here, but I'm quite happy with this. This means that the BMS is quite okay with one of the batteries being somewhat discharged compared to the other ones, and if I throw it on the charging pod it should probably level these up alright. So that's all for today's video. I'm going to put this thing together and throw it onto a charging cradle so it can be used again. If you have any questions, then post them in the comments below. I like it when you write comments. That's all for today. Thanks for watching, and see you in the next one.